All right, so today we're going to be talking about building a CQRS and event sourcing microservice with Akka. Right, so I'm Yeshwanth Kumar. I'm a data engineer at ING, and I'm part of the DAP team. So we are a data analytics platform where we help data scientists and analysts to deploy machine learning models in production, right? And the agenda for the day is quite simple. So we're going to be looking at what is CQRS and event sourcing. And of course, we're going to see how we're going to use this by using Akka, with Akka toolkit, and how we're going to do it. And of course, a bit of code and demo as well. Right. So how many of you have heard about CQRS? Okay, that's a lot. How many of you actually worked or built applications around CQRS? Nice. So I think this would be interesting. So CQRS is just a pattern, an architectural pattern of how you build software, right? And it was made famous by Greg Young, but I first heard it from Martin Fowler's blog. And the idea is quite simple. It basically says that it's a model. You have different models for updating and reading information. That is, your read and the writes are separate, right? And you can go to the link for more information on that. So before we actually try to go deep into CQRS, let's see the normal way, right? How we normally would build application on a daily basis. So there is a simple Django or any front end that you have, and then you have a Android thin client, right? So, and then you're going to have a REST API, and then of course you're going to be needing a persistence layer to store your application state, right? So anytime when a user signs up or when they log in, it goes through that, and then your application state is stored there, right? So it's a simple CRUD. You do create, read, update, delete. No big deal. But there are some problems. As and when you start coding more on this, there are some problems. Number one is, let's say at some point you're trying to make a request to do some asynchronous call. So let's say you're waiting for another system to come up, another service to come up, right? And it's going to take a few seconds to a few minutes. And so what would happen from the UI perspective is that you might have to constantly poll, right? To sort of see whether the system was up or the request was successful. So what eventually happens is there's a lot of things happen. So there'll be a bit of a reloading happening where you need to constantly poll and the UI takes a hit, right? So the pull model is not really that good. This is one example. And of course, the scalability becomes a bit harder as the user grows, right? I mean, you're going to be having an application layer, but then later on, as you add more databases, it's going to become really complex for you to get the data out of it and then try to get new features up and running, right? And of course, the most important thing is the history of all state transitions is lost. For instance, I log into my account, I log into my app, I change my first name, and I change my address. I change my first name again. Now, only the latest state is stored for you. The new ones are not available, right? So it would be nice to have all the state transitions as well. So these are just one of the simple sort of problems that you would have as in when you build your software, right? So I believe you can use CQRS event sourcing pattern to sort of come over that. Okay, so to give you another quick introduction of what CQRS is, so like I said, your writes and your reads are separate. That is, over here in this picture, we saw that your reads and your writes are in the same application, but imagine when you separate them into two different layers, that is, your read is separate and your write is separate, right? And even the database is separate, and then you sync them, right? That sort of becomes your CQRS model. But there are some problems with it, or rather they're not problems, but so your read and write are not always in sync, right? Sometimes your read is behind and write is, they're not exactly in sync, but they're not strictly consistent. They're basically eventually consistent, right? And also, the place where you actually read the data from are not your final source of truth. They are just a view of a projection. They're a materialized view, meaning you could have n number of such different easily queryable tables for each of, let's say you have a simple UI where you have many React components and they're all showing different types of data. each of them could have a separate table, right, where you query from. So it becomes super easy, and they all are just view of a projection. That's it. The model would look something like this, right? So your command model, you write, and then of course you have a lot of events going in, and then you get a materialized view that you read from. Does that make sense? Right. So what event sourcing is that the application doesn't care about the state it stores. Of course, it does have a state, but what it means is that it can. So there are a sequence of events, right? What it means is that when something happens in the system, there are so many. It emits a lot of events out, basically, right? So for instance, you can see the events over there: transaction created, transaction model updated, transaction cancelled, and transaction completed, right? Similarly, when a user logs in or signs up, and they change something, change their name, or they change their address, they're all stored as an immutable log, basically, right? From which we then do certain things to get it and then build our view of projection. Right. So now we saw what is CQRS, we saw what is event sourcing. So now we know that we need to split our read and write layers separately, and we know that we're going to be dealing with emitting a lot of events from these. Now, how do we go about building this? This sounds a bit complex, right? We need to, how do we go about building this? And that's where Akka really sort of helps to do it. So the quick introduction of Akka is that it's based on an actor programming model, right? And what it gives you is that it manages concurrency and asynchronous programming really well for you to quickly build distributed systems. Like an actor basically represents what a human can do and also what a computer can do, basically. You can, right? And of course, it has got message queues, and it does easy signaling amongst themselves really well. To write a simple actor, and that's basically what you do. You just need to extend actor, and receive function over there is just a partial function of any to unit, right? So it receives something, it receives a command or a message, and then it does something, and then it returns back, okay? So with this simple Scala class, you extend an actor, you already have certain constructs that you need for doing asynchronous programming. That is, you already have mailbox enabled, okay? And you also have an address for that actor where you can send message to, and of course the messaging APIs are also enabled. You can do ask and tell, which is synchronous and asynchronous APIs already you have for you to like send between actors, right? And of course, the actor also gives you a proper hierarchy. That is, you can have like parent and children under them. And then, of course, a parent can take care of the children, which is typical in many applications where you can propagate all the way down and you can have a proper hierarchy. And if one child dies, then you can set supervision strategies to see how you can propagate up and stuff like that. It becomes super simple with these simple tools that Akka already gives us. Now, let's see. So let's see how we can use this to sort of build our CQRS event sourcing application. Yeah, before we actually go forwards, I need to give a bit of a terminology. I need to clarify on a terminology. So in domain-driven design, which is just a way to sort of structure your application so that it becomes easy to communicate when you have too many domains in a particular system. So what we mean by entity or an aggregate root is just, so let's say an account, a user, a trade, a transaction, all these becomes entities in our system, meaning they're unique and they have a unique ID, right? So this process over here is basically, this one is a persistent actor or an actor that we previously saw here, right? It receives a command, create X, and of course the state gets updated based on the command, and then it emits n number of events, okay? So the thing is, the state can be lost, it's fine. It's not the ultimate source of truth. The ultimate source of truth is actually the list of events that you get out of it, right? So now we know we can have n number of such actors. So let's say a user signs up, one such actor will be created with a username, right? And the state would be the user's data. And then, of course, there can be an API layer before there. When the user, let's say, updates his second name, then there'll be a update username command comes in, the state gets updated, and even gets emitted out, right? Makes a lot of sense. So that's quite simple how you can do that. But over here, how are you actually going to store these events? You need to persist them in some database, right? Because this becomes the actual source of truth. Because you lose this, you lose all the data that you have about our users and everything else, right? So that's where Akka gives you a persistence layer, right? So this is very similar to your normal that you previously saw the actor. It's just that you extend a persistent actor, right? And you still have the same receive function here that you override. You also have receive command. Basically, it's receive command here because you'll be receiving commands, right? That we saw here. And the persistence ID have to be unique, which represents that user or that transaction in an entity. And a receive recover is basically used because an actor could crash, an entity could crash, and you would need to bring it back to the state it were in, right? So if this crashes, there would have been 5 commands coming in, the user created and then updated 3 times. Now you lost that state here. So basically what this persistent actor would do is it would replay all the events for that specific persistence ID and then come back to the state and then start receiving newer commands. So that way the state is not lost, right? Yeah, so basically now a command comes in, we're able to update the state, and we're able to get n number of list of events. Now we literally need to do persist all in our receive command, pass the list of events, and then pass a function which gets called, which basically updates the actor state. So entities can have a var, and they hold the state. You receive a command, you call persist all in the receive in the case, and you pass the events. You do many operations. You want to create. You can do whatever you want, tell another entity or whatever, and then you call persist all. You pass the set of sequence of events that you want to persist to an external system, and the update would be called, which will update the actor state. Does that make sense? So the persistent layer could be, you could use Kafka, you can use Cassandra, and you can use any other external store, but that is basically immutable log of all the events that we have. So now our application would look something like this. This is just the write layer, right? So yeah, we have our thin clients there, and we have our REST API, and we can create, you can see these, you could call them, this could be entities, different entities in the system. So they receive a command, they update the state, they emit events, and you store them in an event log, right? And likewise, you can have so many such entities. This is a simple example of, let's say, import-export platform where you have some trade transaction, you have a buyer, you have a seller, but you get the idea, right? So this is just the write part. Now to quickly give you an idea about the read part, there are many ways to do it. This picture, I just took it from one of the Kafka Connect, it's not mine, but the idea is that now we have an immutable log of events, right? And we need to basically take the events out, filter them, and then create view of projection. So to give you a simple example, you want to maintain a table of just users. You want just simple, just username, first name, second name, address, and user information. So what you would ideally do is you can just read all the events from the source, that is Cassandra or Kafka, filter out certain specific events, that is the events that we spoke about, run them through, either you can use Kafka streams or Spark jobs to extract them, and then insert them into any database that we want. It could be Postgres, or it could be, if you want to do search, then you can insert them in Elastic and stuff like that. So that becomes a view of projection, right? And usually the materialized views are very, very simple. It would be like just, since we can create so many like that, and because we have the power to basically look back in time, 2 years the system is up, and you're adding a new feature, and you literally want to get a new stat on your page, and all you have to do is deploy a new job where it filters certain events and then start inserting, and your read is already up to date. Now you can start querying and get the actual data, and the system will be up to date for the 2 years it missed. So it becomes super easy to build a lot of such views out of the data that you have. So now we saw how we can do the write layer and the read layer, right? So they are separate. Writes it to a separate source, and the read reads from it, and then you're able to the query layer basically. Right. So now that we know we can use actors to do this, right? We can consider persistent actors or persistent FSM to be entities, and we are able to model it. And of course, actor gives you supervision, like I said, it gives you everything. But how do we scale this, right? So Akka gives you certain ways to do that. That is, you have Akka clustering, and of course you have Akka cluster sharding as well, right? So what clustering does is basically, you can have a 3-node or a 4-node Akka cluster, where your actors basically reside, and Akka cluster sharding is how well you're going to create n number of shard regions for the actors to reside. Okay, so yeah, and to enable clustering, it becomes very, very easy in our system. You literally need to add this configuration in your app, right? Which I'm going to show you in a bit. And yeah, so you just add, so basically it requires a seed node. So you can consider a 4-node setup which hosts these actors, and 1 or 2 would be a seed node, which uses gossip protocol to sort of make all the nodes talk to each other. And even if you want to bring in the 5th node up to this cluster, you literally need to add this. You need to point to the seed node. So when the new node comes up, it talks to this endpoint, and they all talk to each other, and this node becomes part of the cluster, right? So it becomes super easy to also start scaling your Akka cluster by adding new nodes for you. So this is how it works. So A comes in, and the B comes in, and it basically says, A, I want to join. And then they share gossip about other nodes. And then C comes in, it joins. And then, of course, A is going to ask C, did you know about B? Likewise, you can keep adding more nodes, and they will all join the cluster. And also, when you talk about entities, you could have 1,000 actors or 10,000 actors based on how many users you have, right? You can have so many entities, because when you create a new user, when you create a new user, there's a new entity. When you create a new, let's say, transaction, that's a new entity, right, in our system. So how you need a way to sort of distribute that, because manually us doing it is going to get really complex. You want Akka to smartly distribute it among the node in an efficient way. And that's where cluster sharding comes into picture. I'm not going to go too detailed into how the shard region coordinators and how they work internally, but the idea is that you pretty much set a configuration in all your app. For each of your entities, you just say that this entity is part of this cluster, and you just give the configuration, and that's it. You literally send a message to that region. That's an actor ref. You send a message saying a new entity or an existing entity. Akka would automatically either create a new entity for you, or it would forward that message all the way to that actor. So you don't have to worry about sending. You don't have to keep notes of where your specific actor or entity is residing. You send a message to one of the shard region coordinator, and that would redirect it automatically. It would forward the message all the way to, let's say our entity is in shard 3, it will forward it to that basically. So let's look at the demo. So what I have here is, you can see the code. Is it clear? Yeah. Yeah. One sec. No, hold on. Yeah. Oh yeah. Nice. Oh wow. Doesn't like it. Let's just give me a minute. Oops. There you go. So This is the setup. So basically, we have an account entity, right? So this is a simple app. I'm just going to start this app now, which is going to, so this is the cluster that you set up. This is just the configuration that you set up. But the most important part here is this cluster sharding. What you basically specify here is that every entity give a shard name. Let's say you give a shard name to it. And you also give the props, entity props to it, right? Basically, your entity's props, that is, it knows how to start the actor, the properties of it. So, and then of course you also give the ID extractor and the shard resolver. So this is internally used by the region coordinator, like I said, to know where the actor is currently residing, the entity is currently residing. Okay, so let me start. So I'm also going to show you, I'm going to start the same app thrice, and the configuration is that anything running on 2551 will become the seed node automatically, because that's what we have set in the configuration, right? 2551 becomes a seed node. So I'm running the first app. It's a bit slow. Okay. So there you go. It's showing dead letters because it also needs 2552 because I have two seed nodes. I just changed. I'm running the same app in a different port, another node basically. And once, oops. No, it's because Docker is running. Same app. Now you can see that. So as you can see here, the cluster node is joining and it's saying 2552, it's up, meaning they both spoke to each other. I'll start one more node in a random port, just give 0. So this is just a normal, this is not a seed node. So we have two seed nodes, 2551, 2552, and I'm starting another node. Okay, which would, you can see, there you go. Oh no, not yet. 58562. Init join acknowledge message from node 2552. Okay. So now so I'm going to quickly run. I've already have a client app that I can use. Which can quickly show you. Oops. It's right here. So this is just a client app. Instead of having an HTTP layer, which basically this sends the command to that actor, but it's a complete different actor system. Like it's not related to this cluster that we currently have. It's just for testing, right? And I'm just going to start this. This is starting on a random port. And if you see what this does is, this is basically it's just a periodic scheduling that I do. What it does is just every 4 seconds, it just sends a message to that actor. And then to this cluster so that we can see that it's actually persisting the data into an external persistence layer, which is Cassandra in our case. So I'm just going to start the client app, which just keeps sending commands every 4 seconds. Before that, let me just check. This is the old data. I just killed. I'm just starting Docker, starting Cassandra, Docker compose. This should. Okay. Yep, it's up. Sorry. No. Yeah, waiting for gossip to settle. Yeah. So I connect. It's connected. There's nothing in the key space. It's empty. So I'm going to start my client. So we have our cluster running now, a 3-node cluster, and we have the Cassandra up and running. So now I'm going to start sending a lot of commands to this, which will create new entities for you, update the state, and start persisting the events into the event store. Okay? So that's 3-node. Okay. So you can see something is happening. Yeah, it's complaining that it's using Java serialization, which is quite slow, but typically you can use different serialization binary formats, like you can use protobuf or Avro or to actually serialize and deserialize your Scala classes. So now let's go to tbeaver. Let me quickly connect again. And you can see that the Akka snapshot, you can see the tables and you can see the messages. So that's basically all your events. So this is the persistence ID. You can see 444. This is basically, you can see the sequence number here, 1, 2, 3, 4. That is, it's sending like first create and then update, then update. It needs to also keep the sequence number, right? Because let's say number 4 actor, this actor dies, then it needs to basically look at this sequence number till the latest one. It replays everything, brings the state back up, and then takes up the new commands, right? So if you refresh, you can see it's constantly creating new accounts, updating it, and yeah, as you can see here. So this is basically our right part of it, right? And of course, like I said, you can use like a Kafka Connect, or you can use Kafka Streams to basically read from this Cassandra events, filter them, and build your view of projections for your read side. Does that make sense? All right.